Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon, everyone. I'm Joo-young Kim at Extreme Computing Group, and I'm very pleased to introduce Mr. Jin-Wook Oh, who's visiting us from South Korea. Mr. Jin-Wook Oh is a PhD student at Korea Advanced Institute of Science and Technology, KAIST, South Korea. And since 2008, he has been involved with several projects for real-time object recognition processors. His main contribution was hardware realization of artificial intelligence, such as neural networks, fuzzy logic, and reinforcement learning to improve energy efficiency. His talk today will be Intelligent Accelerator for Low-Power Object Recognition. Please welcome Jin-Wook.
Thank you, Joo. Good afternoon. I'm so pleasure to have a presentation in front of you and this company. Today, I'm going to present about Intelligent Accelerator for Low-Power Object Recognition. I'm going to start my presentation with the outline. First, I'm going to give you the introduction to the object recognition and its application. With this slide, I'm going to answer why the object recognition is important and required in today's application. Second, I'm going to explain about the attention-based object recognition processor from our group. We haven't presented 4 processors since 2007 by adopting attention-based object recognition algorithm to the silicon level. But today, we don't have enough time to cover all the processors. Just I want to focus on BOMV4 processor, which have been presented last year. And then I'm going to move on to the Intelligent Accelerator. Intelligent Accelerator is getting its attention to satisfy today's object recognition requirements for real-time operation. So we present the Intelligent Accelerator as Iris this year. So I'm gonna give you the explanation about it. And then I'm going to summarize my talk. Object recognition is widely applied to our daily lives. For example, vehicle safety, intelligent robots, and object recognition-based augmented reality in smartphones and mobile gadgets. We believe that those processors should consume the power lower than 400 milliwatt while processing in real time, so it has to process more than 30 frames per second with VGA image. And also it should be small enough to be integrated SoC platforms. So we believe that those 3 requirements should be satisfied for the mobile applications. But we know that that's very hard job to satisfy those requirements at once. I'm going to explain why with this slide. Object recognition is to find the object instances in the input image, as you can see at the left side. For example, if you try to find the object in database, then in this input image, then there are always background clutter, occlusion, and rotation to each target object. So object recognition should have some kind of immunity to the variance of scale, illumination, rotation, occlusion, and clutter, etc. So we need to require complex algorithms to achieve robustness to sustain certain amount of accuracy, object recognition accuracy. So our approach to solve the problem is to realize low-power real-time object recognition processor in embedded form factor. So we took 2 approaches to solve the problem. First one is algorithm approach. So to reduce the number of computations required for the object recognition processor, we just reduce the computation by adopting visual attention process. Visual attention is a process to focus our vision to a certain area. So we just the algorithm, and we just processing the region of interest, or ROI. So we can reduce the computation from the whole image to a certain region of ROI. And to support this algorithm, we also take the approach of hardware implementation. They are the heterogeneous parallelism to increase the system performance, and also there are also low power management technique to increase the energy efficiency. So from now on, I'm going to explain these technical approaches with the BOM-V4 processor. As I told you before, we have presented 4 processors since 2007 as a real-time object recognition SoC for vision applications. But as you can see here, they have many hardware techniques and new low-power approaches to increase the system energy efficiency and also to sustain the system performance. But today, I want to focus on 2 of them by just looking into the BOM-V4 processor. They are the attention algorithm architecture and the intelligent realization on SoC. So using these 2 techniques, we believe that even for the future object recognition application processor, we can achieve the performance and energy efficiency at the same time. From now on, I'm going to show you the detail. For the BOM-V4 processor, we use the bottom-up salience attention. The bottom-up salience attention uses the intensity, color, and orientation map from the input image, and to detect the most salient point in the input image. So for the attention process, we detect the region of interest in the salience map, which is most salient. So that ROI probably most likely have the target object in input image. But just for the bottom of salience attention, it has some critical limitation. The limitation is that it only works when the object is more salient than background. If the background is more salient or equally salient, then this algorithm must only fail. I'm going to give you an example. What do you see in this image? Can you see a Dalmatian here? This is an example that the spot of target object and the spot of background are equally salient. So using the bottom of salience algorithm, we cannot find the attention point. But I believe that some of you have already familiar with this picture, or you have familiar with, you have experience to recognize the target Dalmatian in here. So from that memory you have experienced, your brain can guide your attention to the target object. This is called top-down familiarity attention. Let me give you a brief introduction of top-down familiarity attention. So to detect the real salient point and real target object in input image, we use prior knowledge to select familiar object to the memory we have. So first of all, it finds a prototype object based on the bottom of salience attention. Then the algorithm evaluates the detected object, whether it is familiar or not. If the object is familiar, then it keeps searching for further verification. But it decides not to be a familiar object, then it searches elsewhere, inhibiting the target object region. So using top-down familiarity attention, we can reduce the number of computation for the object recognition so that we can increase the system performance and power consumption. So to support that algorithm, the BOM-V4 processor have been presented with 4 remarkable hardware features. But today, we don't have enough time to touch all these issues. Just I want to focus on 3 of them, which is strongly related to the intelligence. First of all, the first feature is dual layer architecture, which separate attention and recognition layers to increase energy efficiency and system performance. And second, Intelligent Inference Engine, or IIE, will be explained. As I just told you in previous slide, it is implemented for high attention precision in feedback top-down formulated attention. And last, the power mode control, or PMC, will be explained, which is designed for the low power operation of overall process. So using these key features of BOM-V4, we successfully implemented the processor which is suitable for the mobile environment. I'm going to explain one by one. The first key feature is dual layer architecture. It is composed of cognitive control layer, or CCL, at the top, and the parallel processing layer, or PPL, at the bottom. As the name implies, and also the position implies, the CCL is responsible for the high-level functions of overall chip processing. So it is related to the power mode control and feedback control, which which enhance the system performance and energy efficiency. Otherwise, the parallel processing layer, or PPL, is responsive for the object recognition algorithm. So using the SIMD machine here for VPE and MIMD machine for SPE, the operation with the SIMD and MIMD machine, the PPL conducts the object recognition algorithm to detect the target object. A total of 51 IPs here communicate with the star topology network junction protocol that enhance the communication bandwidth between internal processors and also between the bandwidth between the external chip and the internal processors. Yes, I want to more look into the cognitive control layer, or CCL. As I told you before, it is responsive for the visual attention and task power management. So the 5 main functions performed in the CCL are performed by the CCL. The 32-bit RISC processor executes a host program, and the Global Task Management Unit, or GTMU, assists in top-level recognition task scheduling. Visual Attention 2, or VA2, and Intelligence Inference Engine, or IIE, are responsive for the bottom-up attention and top-down attention, respectively. And also the PMC is changing the supply voltage and frequency of the PPL to minimize the power consumption of the chip. So among these processors, the IIE and feedback, IIE for the feedback attention realization and PMC for power mode control play key role of this whole chip control for the low power energy efficiency, high performance object recognition processor. So I want to describe more with these 2 processors. The second key feature of BOM-V4 for today is Intelligent Inference Engine, or IIE. IIE is a mixed mode implementation of Adaptive Neuro-Fuzzy Inference System, or ANFIS. It is realized by the analog and digital mixed mode system to increase energy efficiency for the over IIE process. It is composed of 2 circuits. One is analog data path, and the other is digital controller. Analog data path is realized for the inference output generation based on the membership function rules and fuzzy rule selection layers. The key components of analog database include the membership function circuit and fuzzy rule layer circuit, which are implemented by the compact and low power analog circuits. They are controlled by the parameters from the digital controller. And the digital controller is composed of parameter database and flexible learning calculator. So using this system, we can implement the intelligence inference engine for over chip processor with energy efficient implementation. So this slide shows the online learning operation of IIE. Online learning enabled the IIE to adapt novel object patterns and the sensor input noises. So that process is composed of 3 steps to minimize difference between the inference result from here and the desired output YD here. The first stage is evaluation. It generates error value which is the difference of the desired output YD and the normal inference value with the normal parameter over here. And second stage for perturbation, it also generates error value but with the perturbed parameters. It is iterated 9 times because there are 9 membership function circuits in analog data path. So for last, parameter update, new weight or new parameters are updated based on the difference between the result of previous 2 stages. So using the hardware efficient perturbation-based learning algorithm, we can iteratively converge the output value YD to the desired output Y, output Y to desired output YD. The next key feature of BOM-V4 is prediction-based parameter power mode controller. This is designed to increase the energy efficiency of the whole processor, especially the PPL, because PPL accounts for 78% of peak power consumption of the whole chip processor. Moreover, it can have up to 5x difference between the maximum and minimum workloads. So the power mode control modifies the operating frequency and the supply voltage of PPL based on the workload prediction by IIE. The IIE, as I told you before, whose primary role is for feedback attention, but in this case, it performs workload prediction based on the previous workload history and the present state. So the PMC improvement on the overall system will be shown on the next slide. As you can see here, this figure shows the operating frequency, the fluctuation of operating frequency, and the supply voltage of over processors. Based on the entry and exit of object in the input image, it changes its transition to the different power control mode. So testing with the 60 second, 30 frames per second video image, it reveals that the PMC with the overall processor is able to reduce the power consumption by 48% with the unified visual attention model, which is the integration model of the top-down attention and bottom-up attention, also the PMC power mode controller, compared to salence-based, salence standalone based attention algorithm. So this slide summarizes the BOM-V4 processor. As you can see here, it is implemented with 1.30 micrometer logic CMOS. It have almost 51 processors it's communicated with by the network protocol. It also adopts DVFS, so it can achieve energy efficiency finally. Yeah. As you may notice, the intelligent inference engine is quite small, only consuming by 1 square millimeter, but it increased overall chip processing performance and energy efficiency, so that we were at the time were shocked that the intelligent inference engine can affect significantly to the overall processor. So from that concept, from the start point of the intelligence, from now on I just want to move on to the intelligent accelerator for more harsh environment object recognition processor. With this slide, I'm going to explain why the intelligence should be integrated to the object recognition. Can you find the target object kangaroo on input image here? It seems that it is not easy even for human to find the target object kangaroo in here. Then what about computer? With the 2.3 gigahertz Xeon processor, it takes more than 1.5 seconds with 80% accuracy, reportedly consuming 50 milliwatt per megahertz. But those numbers are very different from what you expect, the target specification. As the target specification from the previous experience, the speed should be lower, the latency should be lower than 33 milliseconds per frame, and it should be, the accuracy should be higher than 90%. And as a result, the energy efficiency should be higher. Should be high enough with the 2 milliwatt per megahertz. But we believe that this specification getting more difficult to achieve, because for future object recognition application, the input image will be more dynamically changing. So, and with the high resolution video input image. So we thought that as the IEIE for bone briefer processor for present object recognition application, if we adopt Neuro-Fuzzy intelligence for the object recognition processor, we believe that we can fulfill those requirements at once. So from now on, I'm going to explain the basic concept of intelligence that is applied to the object recognition processor, and why it can solve the problem for the object recognition. As the name implies, the Neuro-Fuzzy implies, the artificial neural network is main target of our intelligence. I believe that many of you are already familiar with this artificial neural network or other reinforcement learning algorithms. I want to focus on the main point and the main concept that we apply to our processor. Artificial neural network is a system is composed of the different functional node and the connection. Each node has a discrete output, which is generated from the integration of every connection from the previous layer's nodes. But each node has special function which is called as activation function. So it just evaluates its state value with the nonlinear function to generate the nonlinear function output. So the artificial neural network has some characteristic determined by the complex nonlinear functions. It can generate powerful reasoning operation to the overall processor. But it requires large amount of computations, such as multiplication, integration, and nonlinear functions, so that it is very hard to achieve for the mobile environment, because it needs a large number of computation and complex one. The next target algorithm is fuzzy rule-based system. to describe the fuzzy system, we only need to give the rule base to the prior neural network connections. So we assigned the rule to each node of fuzzy system so that the rule seems like this, as you can see here. But each node, for example, I can give you an example for your information, for your better understand. So if the input of Neuro-Fuzzy system for X is the characteristic of or feature of target object. For example, X1 is size, and X2 is color, and X3 is motion vectors. If the input object is, so the rule can be like this. If the input object is small, and its shape is red, and also it's very slowly move, then it can probably an apple. So the rule is, this is very simplified fuzzy rule. So if we just realize the rule, then the function A to quantify the fuzzy number is very important. That is called as membership function of fuzzy set. That is probably almost same function as activation function in neural network. So A is the most important part of fuzzy rule, and which determines the rule of the fuzzy system. In addition, this is a fuzzy additive system. The output value is weighted average of the whole each node of fuzzy rule system. So determine the discrete output value yk. So let's move on to the learning algorithm. The target learning algorithm of our processor is reinforcement learning. I think many of you are already familiar with reinforcement learning because it's famous for very powerful, and also it can be applied to any application, but it's complex. So we just slightly changed to our system to reduce its computation, and we just make it 4 processes, so that can be accelerated by our hardware one by one. The first process is data preparation. It's a process to generate the training data set from here, from the data pool, by shuffling the data pool to generate a balanced input data set to the local network. So at the second stage, local network can be trained with the generated data set from here. So it updates local parameter of all processor respectively. And at the third stage, real generation stage, it updates policy table to generate reward to each local network, which one is more reliable or suitable to this present task. So the global local update stage or global parameter update stage provides the weight of each local network's result, its kind of confidence or reliability. So using this algorithm with Accelerator, so we can implement this powerful algorithm to our embedded SoC. Yes, this is what we adopted to our system, global reinforcement learning algorithm. I just prepared this slide for your just information. But yeah, I'm not going to cover all the details of reinforcement learning, especially for this presentation. So you can look for information by yourself, and if you have interest more, then you can ask me. The algorithm we adopted is the compositional reinforcement learning for composite Markov distance process. It's based on the localized version of SALSA zero-order algorithm. So it's very simple. It's one kind of temporal difference learning algorithm. So it can be simple to process to generate its results compared to other complex algorithms. we also perform a certain amount of non-greedy exploration to provide more learning efficiency to other system. Yes. From now on, I'm going to show you why this intelligence can be used to meet those requirements or fulfill those requirements for the future object recognition application. First one is speed. If the Neuro-Fuzzy intelligence is adapted for the object recognition processor, it can increase system performance a lot. Let me give you an example. We believe that object recognition is composed of first step for procedure: the region of interest attention, feature extraction, descriptor generation, and feature matching. But with the more complex images for HD and dynamically changing scenes, the ROI cannot just get focused the more important part or more salient part of the input image. So the ROI seems more higher than 7%, which means that it cannot just guide our attention or reduce the number of computations that is unnecessary. So by doing this, the rest of the processor also have large number of computation. For feature extraction, there can be more than 600 features, and the shift descriptor is 128 dimension, and also the matching entry can be more than 40,000. But if we just increase the ROI efficiency by using the powerful Neuro-Fuzzy intelligence, then we can reduce the ROI less than 40%. As a result, we can dramatically reduce this number to this. So as a result, we can achieve real-time operation which consumes less than 30 milliseconds per frame for future object recognition applications. For second requirement, accuracy. Neuro-Fuzzy online learning operation can be increased, can be used for increased recognition accuracy of the object recognition processor. As I told you before, the Neuro-Fuzzy is composed of two steps. First one is inference. Inference is a process to classify query object based on object features. In this case, for example, size, orientation, motion, and position of objects. By modifying the fuzzy rules in the classifier to generate the output confidence between 1 and 0. And for the learning process, is a process to minimize the difference between the desired value in database and the generated confidence. Excuse me, by changing the rules in the classifier sophisticatedly, so the system whole Neuro-Fuzzy classifier is modified for the current task, which is query object. So it can provide more confidence, more reliable confidence results for the present task. So as a result, it can increase recognition accuracy of object recognition more than 90% by online learning adaptation. The last requirement, energy efficiency. Neuro-Fuzzy inference intelligence also can be used to increase energy efficiency. Working as a hardware workload predictor, as II before, Neuro-Fuzzy system can be implemented for the task management unit. It monitors algorithmic parameters, for example, object ID, detected object, and number of ROI, and threads, and processes. Then it changed the hardware specification, it changed the hardware environment by using the DVFS, which means dynamic voltage frequency scaling, and MIMD hardware, parallel hardware configuration, and memory bandwidth between internal cores and external memories. So using this, we can increase energy efficiency of object recognition processor, which consumes less than 2 milliwatt per megahertz for a future object recognition application. So through these slides, we realize that we can increase the system performance and energy efficiency by implementing Neuro-Fuzzy Inference Accelerator to the object recognition processor. So if we can realize intelligent accelerator additionally more efficiently, energy efficiently, then the overall processor or platform can consume less power but perform better than before. So our Neuro-Fuzzy intelligence has these three features. It has high operation speed, and it can provide high learning accuracy, as well as it's energy efficient. For high operation speed, analog P cluster or APEC is designed for the 32 by 32P arrays for matrix operation, which is basic operation of neural network and inference. And second, for high learning accuracy, Global Local Learning Accelerator or GLA is designed for the flexible digital learning implementation. At last, for energy efficient system, Neuro-Fuzzy RISC or NF-RISC is designed to maximize the system throughput of mixed mode system by reducing the delay, communication delay. So finally, we implemented low power portable embedded Neuro-Fuzzy accelerator for object recognition processor. So from now on, I'm just going to explain one by one these features. This slide shows overall system architecture consisting of global local learning accelerator, Neuro-Fuzzy RISC, and memory controller. The digital domain is implemented. Digital system is implemented for flexible learning operations. So in order to provide high learning accuracy, the digital domain is designed. And second, consisting of analog P cluster, normalization circuit, and nonlinear function circuit, analog domain is designed for the Neuro-Fuzzy inference. By implementing high parallel and low power analog MIMD machine, we can realize its parallelism very energy efficiently. At last, two mixed domain system is finally completing the high energy efficiency and also providing accurate recognition results mixed domain system. The first key feature that I want to point out today is analog P cluster or APC. APC consisting of 32 by 32 processing elements or PEs for the energy efficient Neuro-Fuzzy inference realization. Each PE is composed of 16-bit signed multiplying DAC and 16-bit SRAM arrays. The output current from each PE in a column is integrated to the normalization circuit and the nonlinear function layers to provide the inference result to the digital domain system through the ADC. So using this architecture for 32 by 32 matrix operation, it only takes 6 microseconds, which is 11.12x faster than the 16-way SIM processor at 200 megahertz. The next component of IRIS that I want to talk about is Global Local Learning Accelerator. This is designed in the digital domain for the flexible learning algorithm with high performance. It is composed of cross-validation buffer for data preparation, which shuffles input data from data pool, and the learning targeted CPU or SPU for vector calculation of complex learning algorithms, and dedicated hardware for the complex update equation in local parameter update algorithm. So this hardware features balanced architecture of programmable hardware and ASIC accelerator. So using this hardware, we can finally provide 9% accuracy improvement based on high throughput learning acceleration. The first component of GLA is cross-validation buffer. The data shuffle process is performed based on the target object. We can manage our hardware based on its target algorithm. So per object bank management, memory bank management can be applied so that we can reduce 20% power consumption by improved utilization. And for the enter request accelerator, consisting of object rotator and FIFOs, it is designed to for the temporal alignment of our shuffling data. So using this hardware, we can sustain 94% of accuracy for the target object database. The next component of GLA is Learning Targeted Sim Processing Unit, or LSP. This hardware is especially composed of 16-bit 16-array sim machine and the object-based L0 type buffer. So 16-bit 16-way sim machine is controlled by configuration memory, which has algorithm-aware operand forwarding and branch control system, so thereby providing high throughput to the overall processor. And then the object-based L0 type buffer is controlled by the compiler that can provide a 98.2% hit ratio to the LSP. So as a result, 22% throughput increase can be achieved compared to normal sim operation for the learning vector calculation. The last component of GLA is Global Local Parameter Calculator. The Global Parameter Calculator, or GPC, is responsive for the realization of the global parameter update in reinforcement learning. It can generate its policy by lookup table and within a cycle, and also at the next cycle it just generates reward to the neural network. So it can achieve, it can reduce the redundant power processing time for the update. And for the local parameter calculator, or LPC, is designed for the local parameter update, which is parameter perturbation learning, which also that was applied for the intelligent inference engine. That architecture is based on pseudo-random bit generator implemented by linear feedback shifter register, which is 32nd order, to provide enough random bit to the system. Using this specific hardware for the LPC, we can just increase the system throughput for the parameter update, for global local parameter update, faster than 16x faster than sim processing unit. This slide summarizes how the reinforcement learning is implemented in the GLA. At the first stage, for the data preparation, the cross-validation communicates with the memory and it shuffles data. And then next time, for the local parameter calculator update, it provides its shuffle data, which is the training data set, to the GLA and the local parameter calculator. And at third stage, reorder generation, it also, the LSP is responsive for processing the reorder as well as global parameter calculator. Then at the last stage, GPC updates new global parameter update, and it provides the neural network. So implementing all these features for the GLA, we can achieve 36% speed increase for the 9% accuracy improvement than the detailed standalone system, which was presented last year at Boom 4. The last key feature of Intelligence Accelerator is interdomain communication. When you look into the latency for just one learning iteration, we realize that 22.4% of whole processing speed one cycle is related to the interdomain communication between the analog and digital domain. So this time is really unnecessarily spent on the mixed mode system. So we try to reduce this time to meet our system requirement, which is 102.4 gigabps between the CVB and APC. So we adopt this. The Neuro-Fuzzy RISC processor, NF-RISC, is designed to reduce the interdomain communication by the delay prediction. When the instruction is decoded, then from the decoder, then the delay prediction occurs to provide the communication delay to the configuration special function register. That contains Neuro-Fuzzy topology, GLA status, AP status, and communication delay. So based on this communication delay, the mixed mode system operates asynchronously, adopting the handshaking protocol. So we can reduce unnecessary delay prediction. So by adopting the mixed mode architecture with the delay prediction protocol, the 35.7% communication delay can be reduced by this technique for this system. So overall processing speed is dramatically increased. Okay, this slide summarizes the intelligent accelerator. This was implemented with 130 nanometer CMOS technology, consuming 75 milliwatt on average. This chip was the most power efficient processor with the 655 GOPS per watt at the last this year's ISS conference, which is most prestigious conference in our silicon field. So this is reportedly placed #1 place at the low power processor with power efficiency. So to verify our processor, we designed embedded Neuro-Fuzzy acceleration extension with the BOMB4 processor. Communicating with the network-on-chip NOC protocol proposed from our group, the embedded Neuro-Fuzzy accelerator can be integrated object recognition processor. So as a companion IP for robust and fast recognition, we successfully provide high throughput energy efficiency to whole this system. Let me show the demonstrated result with this video. Integrating with the BOMB4, the Iris operate as intelligent accelerator. So we tested our system for 3 cases. First one is occlusion. When the occlusion happens, the previous processor, which is BOMB4, cannot detect the occluded object. But with Iris, because of its powerful intelligence ability, it can recognize the occluded object successfully. And second, for the novel view object, when the target object is exposed with the novel view, then previous processor missed it. But with the Iris, we can recognize because we have implemented reinforcement, which is very powerful and still fast. At the third, background clutter. When background is changing very dramatically, the BOMB4 misguided attention and detection. But the Iris can still find recognize the target object by its powerful learning and intelligent operation. So as a result, we successfully implemented more high performance and energy efficient Neuro-Fuzzy accelerator for the overall processor. Okay, let me summarize my presentation. From our group, Von Brief vision processor, including Von V4, was having presented as a heterogeneous multi-core SoC for object recognition application. As an algorithm approach, it adopted bio-inspired visual attention model for energy efficiency and system throughput. And by the architecture approach, we integrate multi-core processor with the intelligent accelerator, for instance, IIE for the Von V4. And we figure out that the intelligence will be strongly demanded or required for future object recognition. So we designed intelligent accelerator for the vision SoC. It is implemented in the mixing mode and also integrating some semi-custom techniques. We can successfully verify its performance with object recognition processor. So as a result, we made architecture and control solutions for low power and high performance vision SoC for future vision applications. Yeah, this is all I have. Thank you very much. Thank you for your attention.